Alright, welcome to the last page of section 14.5, and we're doing implicit differentiation, a new way of doing implicit differentiation, a cool little trick of how we can implicit differentiate our function. So the chain rule can be used to give a more complex, complete description of the process of implicit differentiation. So suppose that an equation of the form, so say we have a function of with two independent variables equal to 0. But it defines y implicitly as a differentiable function of x. So we're defining y as a function of x, so that y is equal to f of x, where our function is really of x, f of x, and we're going to set that function equal to 0 for all x in the domain of f. If f is differentiable, we can apply case 1 of the chain rule to differentiate both sides of the equation f of xy equal to 0 with respect to x. So since both x and y are functions of x, we obtain this. So our partial of, we'll say cap f of, in this case, x, partial of x, is equal to the partial of f with respect. Let me write the partial a little bit better because I keep writing it as 2. It looks like 2. That's a really good partial. Partial of f with respect to x times the partial of x over the partial of x plus the partial of f with respect to y times the partial of y with respect to x. Now, one thing you need to notice, dx over dx is going to be 1. So there's really a lot of room there for you to write that. So the partial of f over the partial of x does not equal 0. So if that's the case, we solve for dy over dx to obtain. So again, this is all equal to 0. So solving for the partial of y over the partial of x. Actually, I'm sorry, I can write that as, let me rewrite that. That should be dy dx. The reason why I can write it dy dx is because it's a function of just that one variable, so they don't have to do partials to that. And so it's dy over dx. So solving for dy dx, what's going to happen is this is 1, so that goes away. And if this whole thing is equal to 0, then I can just move the partial of f with respect to x on the right side. So I have to subtract that, which is given by that. So minus the partial of f with respect to x, divided by, again, I want to get this by itself, so I'd have to divide by the partial of f with respect to y. And that's how I get dy over dx is equal to negative partial of x divided the partial of our function with respect to x divided by our partial of our function with respect to y. So that's how we obtain. That's a new way to do implicit differentiation. Could be seen as a faster way to do implicit differentiation. So what we're going to do is we want to find dy over dx. And in order to do this, what we want to do is we want to first set our function equal to 0. So we're going to get all of our components to one side. So we're going to say 0 is equal to e to the y sine x minus x minus xy. So now we have our function set equal to 0. And now we want to find dy over dx. So dy over dx. So now let's take negative, the partial derivative of x is going to, here, I'll write it out just so because we have room. The partial derivative of our function with respect to x. So we have negative, and so in the numerator we're going to get the derivative of sine x is just cosine x, so e to the y sine is cosine x minus 1 minus y divided by the derivative of our function with respect to y, so it's going to be e to the y sine of x minus 0 minus x. And you can leave it this way. Just leave it this way. You can get rid of the negative in front by distributing it to the numerator and getting 1 plus y minus e to the y cosine x in the numerator, but that doesn't bother me.